James Webb just revealed the 3D atmosphere of a distant planet. You know, trying to see the atmosphere of a planet 400 light-years away is a bit like trying to read the label on a bottle of wine while your friend is shining a stadium floodlight directly in your face. Except in this case, the floodlight is an actual star, and instead of wine, we're trying to study a gas giant so hot it literally tears water molecules apart. But hey, at least the James Webb Space Telescope doesn't complain about the working conditions. Speaking of incredible working conditions, astronomers have just achieved something that would have seemed like pure science fiction just a decade ago. For the first time in human history, scientists have created a three-dimensional temperature map of a planet orbiting another star. Not a fuzzy blob, not a vague estimate, but an actual map showing different temperature zones across latitude, longitude, and altitude. It's like going from knowing that Earth exists to suddenly having Google Maps for an alien world. Think about that for a moment. When most people hear about exoplanet discoveries, they're hearing about planets detected through wobbles in their parent stars or tiny dips in starlight as a planet passes in front. These are remarkable achievements in themselves. Detecting the gravitational influence of a Jupiter-sized planet from hundreds of light-years away is no small feat. But it's still indirect detection. It's like knowing someone is in the next room because you can hear their footsteps, but you can't actually see them. What we're talking about now is fundamentally different. This is direct characterization. This is being able to say, this part of the planet is 4,500 degrees, that part is 4,800 degrees, and up in the upper atmosphere, it's a comparatively chilly 3,000 degrees. This is being able to identify specific regions where water molecules are being chemically destroyed by heat. This is meteorology for alien worlds. The breakthrough that changed everything. The date was October 28, 2025, when a team of astronomers led by researchers from the University of Maryland and Cornell University published their findings in the prestigious journal Nature Astronomy. What they revealed sent ripples through the scientific community and captured the imagination of space enthusiasts around the world. The planet in question is called WASP-18b, and calling it extreme would be an understatement. Located approximately 400 light-years from Earth in the constellation Phoenix, this massive gas giant is what astronomers classify as an ultra-hot Jupiter. To give you some perspective, WASP-18b has roughly 10 times the mass of Jupiter, our solar system's largest planet. But here's where things get truly wild. While Jupiter takes nearly 12 Earth-years to orbit the Sun, WASP-18b completes its entire orbit in just 23 hours. Yes, you read that correctly. A full year on WASP-18b is shorter than a single day on Earth. This breakneck orbital speed means WASP-18b is incredibly close to its host star, much closer than Mercury is to our Sun. The result? Surface temperatures that approach a staggering 5,000 degrees Fahrenheit. That's about 2,760 degrees Celsius for those of you who prefer metric. To put this in perspective, that's hot enough to vaporize most metals, and as we'll discover, hot enough to do something remarkable to water molecules. To really grasp how extreme WASP-18b is, let's compare it to some familiar reference points. The melting point of iron is about 2,800 degrees Fahrenheit. The surface of the Sun is around 10,000 degrees Fahrenheit. WASP-18b sits squarely in between, hot enough that if you could somehow stand on a solid surface there, you couldn't, it's a gas giant, you'd be bathed in a dull red glow from the heat itself, similar to looking at molten steel. The planet would be glowing like a hot coal. The orbital mechanics of WASP-18b also tell us something profound about its history. Planets don't form this close to their stars. The environment is simply too energetic for solid material to accumulate during the planet formation process. Instead, WASP-18b almost certainly formed much farther out in its solar system, perhaps in a region similar to where Jupiter orbits in our own system. Then, through gravitational interactions with other planets or with the protoplanetary disk of gas and dust, it slowly spiraled inward. This process, called planetary migration, is now thought to be common in exoplanetary systems. WASP-18b is the end result of a long journey that may have taken millions of years, ending with the planet settling into a scorching orbit just a few million miles from its star. Ryan Challoner, a postdoctoral associate in Cornell University's Department of Astronomy and the lead author of the study, explained the significance of their achievement. Eclipse mapping allows us to image exoplanets that we can't see directly because their host stars are too bright, he said. This new technique is going to be applicable to many, many other planets that we can observe with the James Webb Space Telescope. We can start to understand exoplanets in 3D as a population, which is very exciting. To truly appreciate this breakthrough, we need to understand just how difficult it is to study exoplanets, planets orbiting stars other than our Sun. The first confirmed detection of an exoplanet around a Sun-like star only happened in 1995, and since then, we've discovered more than 6,000 of these distant worlds. But discovering they exist and actually studying them in detail are two entirely different challenges. Here's the problem. Planets don't produce their own light. They only reflect, or, in the case of very hot planets, emit light from their heat. An exoplanet typically contributes less than 1% of the total light we see from its star system. For many exoplanets, that figure is less than 0.01%. It's like trying to study a firefly next to a searchlight, except the searchlight is thousands of times brighter and the firefly is hundreds of light years away. For decades, astronomers could only infer the existence of exoplanets through indirect methods. They could watch a star wobble slightly as a planet's gravity tugged on it, or they could measure the tiny dimming that occurs when a planet passes in front of its star from our perspective. These methods told us planets were there and could even give us estimates of their size and mass, but they couldn't tell us much about what these worlds were actually like. The wobble method, technically called radial velocity detection, works because planets and stars orbit their common center of mass. Even though a star is much more massive than its planets, it still gets pulled slightly back and forth by the gravitational tug of orbiting worlds. By measuring the Doppler shift in the star's light, the same effect that makes a passing ambulance siren change pitch, astronomers can detect this wobble and infer the presence of planets. This is how the first exoplanet around a Sun-like star was discovered in 1995, earning its discoverers the Nobel Prize in Physics decades later. The transit method, watching for the dimming of starlight when a planet passes in front of its star, became even more powerful with NASA's Kepler Space Telescope, launched in 2009. Kepler stared at a single patch of sky for years, monitoring the brightness of over 150,000 stars simultaneously. The tiny dips in brightness, typically less than 1% for even a large planet, revealed thousands of exoplanets. But these were still indirect detections. They told us planets existed and gave us their sizes and orbital periods, but not what they were actually like. Spectroscopy, analyzing the spectrum of light to identify chemical fingerprints, began to change that. By carefully studying the light during a planetary transit, astronomers could detect the signature of molecules in the planet's atmosphere as starlight filtered through it. This technique revealed the first atmospheric detections of water vapor, sodium, and other molecules on exoplanets. But these were one-dimensional measurements, giving us average properties across the entire visible hemisphere of a planet. The James Webb Space Telescope, launched on Christmas Day 2021, changed everything. With its enormous 6.5-meter gold-plated mirror and suite of incredibly sensitive infrared instruments, Webb can detect the faint infrared light emitted by hot exoplanets. But even Webb can't take a clear photograph of most exoplanets. The light from their host stars is still far too overwhelming. That's where the genius of eclipse mapping comes in. The technique that enabled this breakthrough is called 3D eclipse mapping, also known as spectroscopic eclipse mapping. The principle is elegant in its simplicity, even if the execution is extraordinarily complex. Here's how it works. Astronomers wait for an exoplanet to pass behind its star from our perspective, an event called a secondary eclipse. As the planet disappears behind the star, different parts of the planet vanish from view at different times. If you're looking at the planet from the side, as it moves behind the star, the left edge disappears first, then the center, then the right edge. During this process, the total light we receive from the system decreases gradually, as more and more of the planet is hidden. But here's the clever part. By measuring extremely precise changes in the brightness at different wavelengths of light as the planet disappears, astronomers can figure out which parts of the planet are emitting which wavelengths. It's like watching a curtain slowly close over a painting and being able to reconstruct what different parts of the painting looked like based on how the overall colour changes as each section disappears. Let's break down exactly how this works with a more detailed example. Imagine WASP 18b as a disk divided into a grid, say 10 sections from left to right. As the planet moves behind its star, the leftmost section disappears first. At that moment, the total infrared light we receive drops by an amount corresponding to how much that leftmost section was emitting. A fraction of a second later, the second section from the left disappears, and the light drops a bit more. This continues until the entire planet is hidden behind the star. Now, here's where it gets really clever. Different wavelengths of infrared light tell us different things about the planet. If we measure this eclipse at a wavelength that water vapor strongly absorbs, say 1.4 micrometers, we're seeing light primarily from the upper atmosphere where water exists. But if we measure at a wavelength that water doesn't absorb much, perhaps 4.5 micrometers, that light can penetrate deeper, showing us lower, hotter atmospheric layers. By measuring the eclipse at dozens of different wavelengths simultaneously and tracking precisely how the brightness at each wavelength changes as different parts of the planet disappear, the astronomers can reconstruct a three-dimensional picture. They can say, in the leftmost section of the planet, at high altitude, the temperature is X degrees, but deeper down, it's Y degrees. Do this for every section of the visible disk, and you have a 3D map. The mathematics behind this reconstruction is complex, involving sophisticated algorithms that have been adapted from medical imaging techniques. It's similar in principle to how a CT scan builds up a 3D image of the inside of your body by taking X-rays from many different angles. Except here, we're getting our different angles by measuring at different wavelengths rather than from different physical viewpoints. You're looking for changes in tiny portions of the planet as they disappear and reappear into view, so it's extraordinarily challenging, Challoner explained. And he wasn't exaggerating. The brightness changes they're measuring are minuscule, fractions of a percent of light that's already less than 1% of the total light from the system. The team's approach built on their earlier work from 2023, when they created a 2D eclipse map of WASP 18b using a single wavelength of infrared light. That first map was groundbreaking in itself, but it could only show temperatures across the planet's surface, like a weather map shows temperatures across a country. It couldn't show how temperature changed with altitude, the vertical dimension. For the new 3D map, the team reanalyzed the same observations from Webb's near-infrared imager and slitless spectrograph, known by its acronym NIRISS, but this time across many different wavelengths. This is where the technique becomes truly three-dimensional. Different wavelengths of infrared light penetrate to different depths in a planet's atmosphere. Some wavelengths are strongly absorbed by water vapor, for instance, so they only show us the uppermost layers where that water exists. Other wavelengths pass right through the water vapor and show us deeper, hotter layers of the atmosphere. This wavelength-dependent penetration happens because molecules absorb light at very specific wavelengths corresponding to their quantum energy levels. Water molecules, for example, have strong absorption features at 1.4, 1.9, and 2.7 micrometers, among others. When infrared light at these wavelengths tries to pass through a region with water vapor, it gets absorbed. The energy goes into making the water molecules vibrate and rotate more energetically. So light at these wavelengths can only escape from the upper atmosphere, where there's not much water vapor above it to absorb it. But at wavelengths where water doesn't absorb much, in the so-called atmospheric windows, light can travel much farther before being absorbed by other molecules or scattered. This light effectively comes from deeper, denser, hotter parts of the atmosphere. By measuring the planet's eclipse at many different wavelengths simultaneously, astronomers are essentially taking slices through the atmosphere at different depths. Some slices show the cool upper atmosphere. Others penetrate to reveal the hot interior layers. Combine all these slices and you get a three-dimensional structure. The NIRISS instrument on Webb is particularly well suited for this because it can observe from 0.8 to 2.8 micrometers covering the near-infrared range, where hot planets like WASP-18b emit lots of light and where many important atmospheric molecules have their strongest signatures. It can also do this in slitless spectroscopy mode, spreading the light out into a spectrum without first filtering it through a narrow slit. This is crucial for eclipse mapping, because you need to capture every photon possible during the brief time the planet is disappearing behind its star. If you build a map at a wavelength that water absorbs, you'll see the water deck in the atmosphere, whereas a wavelength that water does not absorb will probe deeper, Challoner said. If you put those together, you can get a 3D map of the temperatures in this atmosphere. It's remarkably similar to how medical CT scans work, building up a three-dimensional picture from multiple two-dimensional slices, except in this case, the slices are created using different colours of invisible infrared light, and the patient is a gas giant planet 400 light-years away. The 3D map of WASP-18b revealed a world of striking contrasts and confirmed some predictions while revealing surprises. The planet is tidally locked to its star, meaning the same side always faces the star, just as the same side of our moon always faces Earth. This creates a permanent day side that's constantly baked by stellar radiation and a night side in perpetual darkness. The 3D map focuses on the day side, since that's the hemisphere that emits the most infrared light. At the centre of the day side, directly facing the star, the map revealed a circular hotspot where temperatures reach their peak. This is where the star's light hits most directly, and it's scorching hot, even by the standards of ultra-hot Jupiters. Surrounding this central hotspot is a cooler ring near what astronomers call the planet's limbs, the edges of the visible disk as we see it from Earth. Now, cooler is a relative term here. We're still talking about temperatures that would instantly vaporize you, me, and everything we've ever known. But compared to the central hotspot, these outer regions are several hundred degrees cooler. The temperature difference tells us something important about the planet's atmosphere. The winds aren't strong enough to redistribute the heat efficiently. On Jupiter, powerful jet streams mix the atmosphere and create relatively uniform temperatures around each latitude. But on WASP-18b, the heat stays concentrated where the star's rays hit most directly. The map also revealed temperature changes with altitude. The upper atmosphere is cooler than the deeper layers, which makes sense. You're farther from the main heat source at the planet's core and the absorbed stellar radiation. This vertical temperature structure gives scientists crucial information about how the atmosphere is layered and how heat moves through it. But the most remarkable discovery was what the map revealed about water vapour, or rather, the lack of it in certain regions. Across most of WASP-18b's atmosphere, the spectroscopic signatures indicated the presence of water vapour, just as theory predicted. At these extreme temperatures, any water molecules that might have been locked in ice or liquid during the planet's formation would have long since evaporated into gas. But in the central hotspot, something strange appeared in the data. The water vapour signatures were significantly weaker than in the surrounding regions. At first glance, this might seem puzzling. If the hotspot is the hottest part of the atmosphere, shouldn't there be even more water vapour there? The answer lies in the chemistry of what happens when things get really, really hot. Water molecules, as you probably know, consist of two hydrogen atoms bonded to one oxygen atom, H2O. These bonds are quite strong by molecular standards, which is why water is stable across a wide range of temperatures on Earth. But there's a limit to how much heat those bonds can withstand. At the temperatures in WASP-18b's central hotspot, approaching 5,000 degrees Fahrenheit, the thermal energy becomes so intense that it literally tears water molecules apart. Hydrogen-oxygen bonds break, and instead of water vapour, you get separate hydrogen and oxygen atoms, or perhaps hydroxyl radicals, OH, if some of the bonds remain partially intact. This process, called thermal dissociation or pyrolysis, is all about energy. Chemical bonds are held together by electromagnetic forces between atoms, and these bonds have specific strengths. The OH bonds in water are quite strong. It takes about 460 kilojoules per mole to break them. At normal Earth temperatures, the random thermal motion of molecules simply doesn't have enough energy to break these bonds. That's why water is stable as a liquid or gas across the temperature range we experience on Earth. But temperature is really just a measure of the average kinetic energy of molecules. As things get hotter, molecules move faster and collide more violently. At the extreme temperatures in WASP-18b's hotspot, when water molecules slam into each other or into other atmospheric constituents, those collisions carry enough energy to actually rupture the chemical bonds. What happens to the water after it's torn apart? The hydrogen and oxygen don't just sit there as separate atoms. In the intense heat and chaos of WASP-18b's atmosphere, they can recombine in various ways. Some hydrogen atoms pair up to form molecular hydrogen, H2, the most abundant molecule in the planet's atmosphere. Oxygen atoms might form molecular oxygen, O2, or they might react with carbon to form carbon monoxide, CO, or carbon dioxide, CO2. Hydroxyl radicals, OH, water molecules that have lost one hydrogen atom, are highly reactive and quickly participate in other chemical reactions. The result is a complex atmospheric chemistry that varies dramatically from region to region on the planet. In the cooler outer regions, water vapor is stable and abundant, but in the central hotspot, water essentially doesn't exist. Instead, you have a cocktail of its constituent atoms and the products of their subsequent reactions. We think that's evidence that the planet is so hot in this region that it's starting to break down the water, Challoner said. That had been predicted by theory, but it's really exciting to actually see this with real observations. Megan Weiner-Mansfield, an assistant professor of astronomy at the University of Maryland, who co-led the project, elaborated on the significance of this finding. We've seen this happen on a population level, where you can see a cooler planet that has water, and then a hotter planet that doesn't have water, she explained. But this is the first time we've seen this be broken across one planet instead. It's one atmosphere, but we see cooler regions that have water and hotter regions where the water's being broken apart. This observation provides powerful confirmation of theoretical models of ultra-hot Jupiter atmospheres. For years, atmospheric chemists had predicted that water molecules would dissociate at these extreme temperatures. But seeing it actually happen on a real planet, mapped in 3 dimensions, is something else entirely. It's the difference between predicting that a snowball will melt in a furnace and actually watching it happen. The detection also demonstrates the incredible sensitivity of the James Webb Space Telescope. To distinguish between regions with intact water molecules and regions where those molecules have been torn apart, while measuring tiny fractions of light from a planet 400 light-years away, requires instruments of almost unimaginable precision. You might wonder why astronomers chose WASP-18b for this pioneering observation. After all, there are thousands of known exoplanets, including many that might be more Earth-like or potentially habitable. The answer comes down to practicality and the need to prove the technique works. WASP-18b is, in many ways, the ideal candidate for testing 3D eclipse mapping. Its size, 10 times Jupiter's mass, means it emits a relatively strong infrared signal. Its incredibly short 23-hour orbit means eclipses happen frequently, allowing for multiple observations in a reasonable amount of time. Its extreme temperatures mean it's emitting lots of infrared light, making the signal easier to detect above the noise. Perhaps most importantly, WASP-18b is tidally locked and has a very clear day-side temperature structure. There's no ambiguity about which hemisphere is being studied. The planet isn't rotating during the observation, which would smear out the temperature patterns. Everything about WASP-18b makes it about as straightforward as eclipse mapping can get, and it's still extraordinarily challenging. The planet's short orbital period is particularly advantageous. Every 23 hours, WASP-18b completes an orbit and passes behind its star, providing a new opportunity for eclipse observations. Compare this to a planet with a year-long orbit. You'd get only one chance per year to observe an eclipse, and if weather, technical problems or scheduling conflicts interfered with that single opportunity, you'd have to wait another year for the next chance. With WASP-18b, if one eclipse observation doesn't work out perfectly, another opportunity comes along the next day. The planet's size is another crucial factor. With 10 times Jupiter's mass and a correspondingly large radius, WASP-18b has a big surface area, emitting infrared light. This means the signal is stronger, not easy to detect by any means, but feasible with Webb's sensitivity. A smaller planet, say one just twice Earth's size, would emit far less total infrared light. making the tiny variations during an eclipse much harder to measure. The host star itself is also well suited for these observations. WASP-18, the star that WASP-18b orbits, is an F-type main sequence star, somewhat hotter and brighter than our Sun. Importantly, it's not so active that stellar flares or spots would confuse the measurements. Some stars, particularly younger red dwarfs, have significant variability in their brightness that can overwhelm the tiny signals from planetary eclipses. WASP-18 is stable enough that the team could confidently attribute the light variations they observed to the planet itself. WASP-18b provided a relatively strong signal, making it a good test case for the new mapping technique, the researchers noted in their paper. It's like testing a new telescope by looking at the brightest star in the sky before pointing it at dimmer, more distant objects. The success with WASP-18b opens the door to applying this technique to other planets. The research team is already making plans to observe other hot Jupiters, and eventually, they hope to attempt 3D eclipse mapping of smaller, cooler planets, perhaps even rocky worlds more similar to Earth. This achievement doesn't exist in isolation. It's part of a broader revolution in exoplanet science that's been unfolding since the James Webb Space Telescope began operations. In previous studies, Webb has detected various molecules in exoplanet atmospheres, including carbon dioxide, methane, sulfur dioxide, and even silicate clouds, essentially vaporized sand. Each detection adds another piece to the puzzle of how these distant worlds work. The detection of sulfur dioxide on exoplanets was particularly exciting because it requires photochemistry, chemical reactions driven by light from the star. On Earth, sulfur dioxide in the atmosphere comes primarily from volcanoes and human industrial activity. But on hot gas giants, it forms when stellar ultraviolet light breaks apart other sulfur-bearing molecules. Finding sulfur dioxide confirmed that we can detect not just molecules that were present when the planet formed, but also products of ongoing chemical processes. The silicate clouds are another fascinating discovery. On some ultra-hot Jupiters, the temperatures are high enough to vaporize silicon-bearing rocks. These gaseous silicates can then condense at slightly higher altitudes where it's cooler, forming clouds of what is essentially vaporized sand. Imagine clouds made of tiny droplets of molten rock instead of water vapor. That's what exists on some of these extreme worlds. For instance, in early 2025, Webb captured direct images of carbon dioxide in the atmospheres of giant planets in the HR 8799 system, confirming that these worlds formed through core accretion, the same process that built Jupiter and Saturn. In another study, Webb examined TOI 421b, a sub-Neptune-sized planet, revealing a clear atmosphere free of the hazes that obscure many similar worlds. The clarity of TOI 421b's atmosphere was a surprise. Many sub-Neptune exoplanets show atmospheric hazes, layers of tiny particles that scatter light and prevent us from seeing deeper into the atmosphere. These hazes can be made of various materials: photochemical smog similar to those on Saturn's moon Titan, or perhaps salt crystals or other minerals formed from evaporated clouds. TOI 421b appears to be hot enough that many haze-forming materials remain in vapor form rather than condensing into particles, allowing astronomers to peer deep into its atmosphere and measure its composition directly. The telescope has also been studying the famous TRAPPIST-1 system, which contains 7 Earth-sized rocky planets orbiting a small, cool star just 40 light-years away. While those observations haven't yet confirmed the presence of atmospheres, rocky planets close to their stars are prone to losing their atmospheres to stellar radiation. They're pushing the boundaries of what's possible. Each of these observations uses different techniques suited to different types of planets. For planets that pass in front of their stars, transmission spectroscopy analyzes how starlight filters through the planet's atmosphere. For planets that we can image directly, their own light can be analysed. And now, with eclipse mapping, we have a new tool for studying planets that are too close to their stars for direct imaging, but that emit enough infrared light to be studied as they pass behind their stars. The development of 3D eclipse mapping represents a maturation of exoplanet science. We're moving beyond simply detecting these worlds and cataloguing their basic properties. We're beginning to understand them as complex, dynamic systems with their own weather patterns, chemical processes, and atmospheric circulation. None of this would be possible without the extraordinary capabilities of the James Webb Space Telescope. Let's take a moment to appreciate the engineering marvel that made this discovery possible. Webb's primary mirror is 6.5 meters in diameter, nearly 3 times the size of the Hubble Space Telescope's mirror. That larger mirror collects more light, allowing Webb to see fainter objects and detect more subtle variations in brightness. But size alone isn't enough. The mirror also needs to be nearly perfect in shape, accurate to within a fraction of a wavelength of light. Achieving this precision for such a large mirror presented enormous engineering challenges. Rather than building one massive mirror, Webb's primary mirror consists of 18 hexagonal segments, each 1.3 meters across. These segments are made of beryllium, a metal chosen for its low weight, high stiffness, and excellent performance at extremely cold temperatures. Each segment was polished to exquisite precision, with surface irregularities no larger than a few tens of nanometers, far smaller than a wavelength of visible light. But here's where it gets even more impressive. Each of these 18 segments has 7 tiny motors on its back that can adjust its position with incredible precision. This is necessary because the telescope had to be folded up to fit inside the rocket that launched it, then carefully unfolded in space. The segmented mirror design allowed Webb to launch with a much larger mirror than would have been possible with a single piece. Once in space, mission controllers spent months aligning these 18 segments so they act as a single, perfect mirror. Using a process called wavefront sensing, they measured how the reflected light from each segment interfered with light from the others, then used the motors to adjust each segment's position and tilt by tiny fractions of a millimeter. The result is a mirror that performs as if it were carved from a single piece of glass, despite being assembled from 18 separate pieces that were folded, launched through space, and unfolded millions of miles from Earth. The mirror is coated with a microscopically thin layer of gold because gold is highly reflective in the infrared wavelengths that Webb observes. This is crucial because hot objects like WASP-18b emit most of their light in the infrared, invisible to human eyes but detectable by specialized instruments. Webb orbits at a point called the second Lagrange point, or L2, about 1 million miles from Earth on the side opposite the Sun. At this location, Earth and the Sun are always in the same direction, allowing Webb's massive sun shield, about the size of a tennis court, to block their light and heat simultaneously. This keeps the telescope's instruments incredibly cold, around -380 degrees Fahrenheit, which is essential for detecting faint infrared signals without being overwhelmed by the telescope's own heat. The NIRISS instrument that captured the observations of WASP-18b is particularly well suited for studying exoplanet atmospheres. It can observe in slitless spectroscopy mode, which means it captures the entire spectrum of light, all the colors or wavelengths, simultaneously, without needing to pass the light through a narrow slit first. This allows for more efficient observations and is ideal for the precise timing required for eclipse mapping. Every aspect of Webb's design, from its mirror segments to its cooling system to its orbital position, contributes to making observations like this 3D map possible. It's a triumph of engineering as much as a triumph of astronomy. The successful mapping of WASP-18b's atmosphere in 3 dimensions isn't just a single impressive result. It's a proof of concept that opens up new possibilities for studying exoplanets. This technique is really the only one that can probe all 3 dimensions at once: latitude, longitude, and altitude, Mansfield explained. This gives us a higher level of detail than we've ever had to study these celestial bodies. In the near term, astronomers plan to apply 3D eclipse mapping to other hot Jupiters. There are hundreds of these massive, scorching planets in the known exoplanet population, each with its own unique characteristics. Some have strong winds that redistribute heat, while others, like WASP-18b, have relatively stagnant atmospheres. Some have clouds of vaporized minerals, others are relatively clear. By mapping many of these planets, astronomers can begin to understand the full diversity of hot Jupiter atmospheres and what causes their differences. One particularly interesting class of hot Jupiters are those with strong atmospheric winds. Unlike WASP-18b, where heat stays concentrated in the central hotspot, some hot Jupiters have powerful jet streams that carry heat from the day side toward the night side. These winds can be thousands of miles per hour, far faster than anything seen in our solar system. The fastest winds ever measured on Jupiter are around 400 miles per hour, but models suggest that some hot Jupiters might have winds exceeding 10,000 miles per hour. Imagine trying to do weather forecasting for a planet where a hurricane-force wind is the baseline condition everywhere. By mapping the temperature structure of many hot Jupiters, astronomers hope to understand what controls wind strength. Is it the amount of stellar radiation the planet receives, the planet's rotation rate, the atmospheric composition? These are fundamental questions about how planetary atmospheres work, and 3D eclipse mapping is giving us the tools to answer them. Another interesting application is studying the night sides of tidally locked planets. WASP-18b's night side, eternally facing away from its star, is much cooler than the day side. But exactly how cool, and how that cooling varies with position and altitude, can tell us about heat transport in the atmosphere. Does any heat make it around to the night side, or is it utterly frigid there? Eclipse mapping of the reappearance of the planet from behind the star can begin to answer these questions. But the really exciting prospect is applying this technique to smaller, cooler planets. Earth-sized rocky planets don't emit much infrared light, making them much more challenging targets. However, planets somewhat larger than Earth, often called super-Earths or sub-Neptunes, might be amenable to 3D eclipse mapping if they're hot enough to emit a detectable signal. Mansfield is optimistic about these future possibilities. It's very exciting to finally have the tools to see and map out the temperatures of a different planet in this much detail, she said. It's set us up to possibly use the technique on other types of exoplanets. For example, if a planet doesn't have an atmosphere, we can still use the technique to map the temperature of the surface itself to possibly understand its composition. Even for airless rocky planets, eclipse mapping could reveal surface features through temperature differences. Hot deserts would look different from cooler highlands, and volcanic regions would stand out as hotspots. It's like thermal imaging, but for entire exoplanets. Additional observations of WASP-18b itself could improve the spatial resolution of the map, revealing finer details of the atmospheric structure. The first 3D map is impressive, but it's also relatively coarse by the standards of what might eventually be possible. With more observation time and refined analysis techniques, future maps could reveal smaller temperature variations and more complex atmospheric features. While the achievement is remarkable, it's important to understand its limitations and the challenges that remain. First, eclipse mapping only works for planets that pass behind their stars from our perspective. This is a matter of geometric alignment. We need to be positioned just right so that we can watch the planet disappear and reappear. Many exoplanets, perhaps most, don't have orbits aligned this way from our viewpoint. For those planets, other techniques will be needed. Second, the technique currently works best for very hot, large planets that emit strong infrared signals. Cooler, smaller planets will require much longer observation times and more sophisticated analysis to achieve similar results. There's a reason WASP-18b was chosen as the test case. It represents something close to the best-case scenario. Third, even with Webb's extraordinary capabilities, the spatial resolution of these maps is limited. The 3D map of WASP-18b shows broad temperature zones and vertical structure, but it can't reveal fine details like individual storm systems or small-scale atmospheric features. The planet is simply too far away and too small in angular size for that level of detail. There's also the challenge of interpretation. When we observe temperature differences and chemical variations in an exoplanet atmosphere, figuring out what's causing those differences requires complex atmospheric models. Is a hot region hot because it's receiving more stellar radiation, because it has different chemicals that absorb heat more efficiently, or because of atmospheric dynamics that concentrate heat there? Untangling these factors requires careful analysis and comparison with theoretical predictions. Finally, there are practical limitations of telescope time. The James Webb Space Telescope is the most sought-after observatory in astronomy, with far more proposed observations than available time. Every hour spent observing WASP-18b is an hour not spent studying distant galaxies, the atmospheres of planets in our solar system, or any of the countless other fascinating targets astronomers want to observe. Despite these challenges, the successful demonstration of 3D eclipse mapping represents a major step forward. As techniques improve and future telescopes become available, these limitations will gradually be overcome. You might be thinking, okay, so we mapped the atmosphere of a hellish gas giant 400 light-years away. That's cool, but why should I care? Fair question. Let me explain why this matters, not just to astronomers, but to our broader understanding of the universe and our place in it. First, every technique we develop for studying exoplanets brings us closer to answering one of humanity's most profound questions. Are we alone? While WASP-18b itself is utterly inhospitable to life as we know it, the techniques being perfected on planets like this will eventually be applied to more temperate worlds. The better we understand how to characterize exoplanet atmospheres, the better equipped we'll be to recognize biosignatures, chemical signs of life, when we find them. What would biosignatures look like? On Earth, the most obvious atmospheric biosignature is the combination of oxygen and methane. Oxygen is highly reactive and would quickly disappear from Earth's atmosphere if plants and photosynthetic microorganisms weren't constantly replenishing it. Methane is also destroyed relatively quickly by reactions with oxygen and by ultraviolet light. The fact that Earth's atmosphere contains significant amounts of both gases simultaneously is a strong indicator that something, life, is actively producing them. If we found a rocky planet in the habitable zone of its star, with an atmosphere containing both oxygen and methane, that would be extraordinarily exciting. It wouldn't be definitive proof of life. There might be geological processes that could produce such an atmosphere, but it would be a very strong candidate for follow-up study. The techniques we're developing now, like 3D eclipse mapping, could potentially detect not just the presence of these gases, but their distribution across the planet. Does the oxygen concentration vary with latitude? Are there seasonal changes? Such details could help distinguish between biological and non-biological sources. Second, studying extreme planets like WASP-18b helps us understand the full range of what's possible in planetary science. Every planet teaches us something about how planets form, evolve, and behave. WASP-18b shows us what happens when a gas giant forms too close to its star, or migrates inward after formation. The thermal dissociation of water molecules in its hotspot teaches us about atmospheric chemistry under extreme conditions. All of this knowledge helps us build better models of planetary systems, including our own. Third, there's something profound about the simple act of mapping another world in 3 dimensions. For most of human history, the stars were just points of light, utterly mysterious and unreachable. Even planets in our own solar system were fuzzy disks through telescopes until the space age. Now, we're creating detailed maps of planets so distant that their light takes 4 centuries to reach us. That's not just scientifically valuable, it's culturally and philosophically significant. We're also developing the tools and techniques that future generations will use to explore the galaxy. The James Webb Space Telescope will likely operate for another decade or two, but the techniques developed using Webb will inform the design and operation of future telescopes. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will carry its own exoplanet imaging capabilities. Ground-based extremely large telescopes currently under construction will have unprecedented light-gathering power. Each new facility will build on the lessons learned from Webb. While WASP-18b is radically different from any planet in our solar system, studying it actually helps us understand our cosmic neighbors better. The same eclipse mapping technique that revealed WASP-18b's 3D structure is being used to study atmospheric variations in Jupiter, Saturn, and even smaller bodies in our own solar system. The principles are the same, even if the targets are much closer and easier to observe. Observations of exoplanet atmospheres also provide context for solar system planets. When we see how heat is distributed in WASP-18b's atmosphere and compare it to Jupiter's more uniform temperature distribution, we learn about the factors that control atmospheric circulation. Why does Jupiter have such strong zonal winds that create its banded appearance, while WASP-18b's winds seem weaker? The answer probably relates to factors like rotation rate, internal heat, and the intensity of stellar radiation. all things we can study by comparing many different planets. The dissociation of water molecules on WASP-18b might seem exotic, but similar chemistry occurs in our own solar system, just in different contexts. In the upper atmospheres of all the giant planets, intense ultraviolet radiation from the Sun breaks apart molecules. In the atmospheres of Venus and Mars, chemistry driven by sunlight plays a crucial role in determining atmospheric composition. Understanding these processes on exoplanets gives us new perspectives on our own planetary neighborhood. There's even a connection to Earth. While our planet is obviously far cooler and more hospitable than WASP-18b, the tools being developed to study exoplanet atmospheres can also be turned toward Earth. Satellite observations of our own planet use similar principles, measuring light at different wavelengths to map temperature, humidity, and atmospheric composition. The better we get at characterizing atmospheres in general, the better we understand Earth's climate system. Behind every scientific breakthrough are the people who made it happen. The Nature Astronomy paper listing the WASP-18b discovery has more than 30 co-authors from institutions around the world. This is typical of modern astronomy, which often requires large collaborations to succeed. Ryan Challoner, the lead author, is a postdoctoral researcher, a position held by scientists in the early stages of their careers after completing their PhD, but before securing a permanent faculty position. Postdocs often do the detailed, technical work of analyzing data and developing new techniques. Challoner's expertise in eclipse mapping and his painstaking analysis of the Webb observations were crucial to this discovery. Megan Weiner-Mansfield, who co-led the project, has been working toward observations like this for years. I had been waiting my entire career for Webb so that we could meaningfully characterize the atmospheres of these smaller planets, she said in an earlier interview about different Webb observations. For scientists like Mansfield, Webb represents the culmination of years of preparation and the opening of new frontiers to explore. The team also includes graduate students, established professors, instrument scientists, and theorists. Some team members helped design and build the NIRISS instrument. Others developed the atmospheric models needed to interpret the observations. Still others worked on the observation planning, figuring out exactly when to point Webb at WASP-18b and for how long. This kind of collaboration is one of science's great strengths. No single person could have made this discovery alone. It required expertise in instrumentation, observational astronomy, data analysis, atmospheric modeling, and more. By working together, sharing knowledge and skills, the team achieved something none of them could have accomplished individually. There's also a broader collaboration worth mentioning. The James Webb Space Telescope itself is an international project involving NASA, the European Space Agency, and the Canadian Space Agency. Scientists from all three agencies and from institutions around the world can propose observations and receive telescope time based on the scientific merit of their ideas. The data from Webb is made publicly available, allowing researchers everywhere to contribute to our understanding of the universe. The successful 3D mapping of WASP-18b is just the beginning. Several exciting developments are already in the works or on the horizon. Additional observations of WASP-18b itself are planned or being considered. With more data, astronomers can improve the spatial resolution of the map and potentially detect time variations in the atmosphere. Does the temperature structure change over time? Are there storm systems that develop and dissipate? These questions might be answerable with more extensive monitoring. The technique will be applied to other hot Jupiters, building up a population study of these extreme worlds. Each planet will have its own unique characteristics, and by comparing many planets, astronomers can identify patterns and test theories about what controls atmospheric properties. Attempts will be made to extend eclipse mapping to cooler, smaller planets. This is technically challenging, but the potential rewards are enormous. Imagine creating a 3D temperature map of a planet just twice Earth's size, orbiting in the habitable zone of its star. Such observations could reveal whether the planet has an atmosphere, what that atmosphere is made of, and how temperature varies across its surface. All crucial information for assessing habitability. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will complement Webb's capabilities with different instruments and observing strategies. Roman is designed to study exoplanets through direct imaging and could potentially work in tandem with Webb to provide even more detailed characterizations of distant worlds. Further in the future, astronomers dream of even more ambitious projects. Concepts exist for space telescopes large enough to directly image Earth-sized planets around nearby stars and study their atmospheres in detail. Some designs even include the possibility of detecting surface features, continents and oceans on alien worlds. These missions are still decades away, but the techniques being developed now with Webb will inform their design and operation. Ground-based astronomy is also advancing rapidly. The extremely large telescope under construction in Chile will have a primary mirror 39 meters in diameter, 6 times larger than Webb's mirror. While ground-based telescopes have to contend with Earth's atmosphere blurring their view, adaptive optics systems can partially compensate, and their sheer size gives them enormous light-gathering power. Working together, space-based and ground-based facilities will provide complementary perspectives on exoplanets. The 3D mapping of WASP-18b represents more than just another exoplanet observation. It marks the beginning of a new era in which we can study the atmospheres of distant planets with a level of detail previously reserved for worlds in our own solar system. We're no longer limited to simply knowing that a planet exists, or even to getting rough estimates of its temperature and composition. We can now map temperature variations across its surface and with altitude. We can watch molecules being torn apart by extreme heat. We can begin to understand these worlds as complex, dynamic systems, rather than just points of data in a catalogue. This progress has been remarkably rapid. The first confirmed exoplanet around a Sun-like star was discovered in 1995. Just 30 years later, we're creating three-dimensional atmospheric maps of these worlds. That's an extraordinary acceleration in our capabilities, driven by technological advances like the James Webb Space Telescope and clever techniques like eclipse mapping. But in another sense, we're still at the very beginning of exoplanet science. With more than 6,000 confirmed exoplanets and likely billions of planets in our galaxy alone, we've only just scratched the surface. Each new discovery raises new questions. Each new technique opens new avenues of investigation. The 3D map of WASP-18b is a milestone, certainly, but it's a milestone on a much longer journey. The journey to understand the diversity of worlds in our universe, to find out if life exists beyond Earth, and ultimately, to understand our place in the cosmos. As we stand in 2025, looking at a detailed three-dimensional map of a planet 400 light-years away, it's worth taking a moment to appreciate how far we've come, and how far we still have to go. The universe is vast and full of wonders, and we're only beginning to explore it. There's something deeply moving about achievements like the mapping of WASP-18b. In an age often dominated by cynicism and immediate concerns, astronomy reminds us that we're capable of remarkable things. We're a species that can send a telescope into space, position it 1,000,000 miles from Earth, keep it colder than the depths of interstellar space, and use it to map the atmosphere of a planet so distant that its light began its journey to us before the Pilgrims landed at Plymouth Rock. We're a species that can work together across national boundaries, sharing knowledge and resources to achieve what no individual or single nation could accomplish alone. We're a species that remains curious about the universe, that asks questions for no reason other than the desire to understand. The 3D map of WASP-18b won't cure any diseases, won't solve any immediate practical problems, won't put food on anyone's table, but it does something equally important. It expands our horizons and reminds us that we're part of something much larger than ourselves. Every time we look up at the night sky, we're looking at a galaxy full of worlds, most of them profoundly different from Earth, many of them beyond our wildest imaginings. Thanks to the work of scientists like Ryan Challoner and Megan Weiner-Mansfield, and thanks to instruments like the James Webb Space Telescope, we're finally beginning to see those worlds not as abstract concepts, but as real places with their own landscapes, their own weather, their own stories. Consider what this means in historical context. For thousands of years, humans looked at the stars and wondered what they were. Were they holes in a cosmic ceiling? Were they other suns? Were there worlds around them? These questions, debated by philosophers from ancient Greece to Renaissance Europe, remained purely speculative until very recently. Even a century ago, we didn't know for certain that our Milky Way galaxy was just one of billions of galaxies in the universe. We didn't know if planets were common or rare. The idea of other worlds was pure philosophy and science fiction. Now, in 2025, we can not only confirm that planets are common, probably outnumbering stars in our galaxy, but we can map their atmospheres in 3 dimensions, watch their weather systems, and analyze their chemistry from hundreds of light years away. This transformation in our understanding has happened within a single human lifetime. People alive today remember when we didn't know for certain that any exoplanets existed, and now we're mapping their atmospheres. WASP-18b, with its searing temperatures and torn-apart water molecules, is one of those stories. It's a world of extremes, a cautionary tale of what happens when a planet forms too close to its star. But it's also a testament to the power of human ingenuity and our capacity for wonder. The map of WASP-18b is more than scientific data. It's a portrait of an alien world, painted in invisible infrared light and translated into temperatures and altitudes. It's a message from across the vast distances of space, telling us that the universe is even more diverse and fascinating than we imagined. And the best part? This is just the beginning. As techniques improve, as more data accumulates, as new telescopes join the search, we'll create maps of more and more worlds. Some will be hot Jupiters like WASP-18b. Others will be rocky super-Earths, ice giants, or types of planets we haven't even classified yet. Each one will teach us something new about how planets work, how atmospheres behave, how worlds form and evolve. And eventually, inevitably, we'll map a world that shows signs of life. A planet with an atmosphere full of oxygen and methane, chemicals that shouldn't coexist unless something is actively producing them. When that day comes, and it will come, we'll look back at achievements like the 3D mapping of WASP-18b and recognize them as the first steps on a much longer journey. The journey to understand not just our cosmic neighborhood, but the possibility of life throughout the universe. For now, we can marvel at what's been achieved and look forward to what comes next. The James Webb Space Telescope continues to observe. Astronomers continue to analyze data and develop new techniques, and our understanding of exoplanets continues to grow with each passing year. The universe is vast, full of wonders we're only beginning to discover. Thanks to the remarkable achievement of mapping WASP-18b's atmosphere in 3 dimensions, we're one step closer to understanding those wonders. And, in a universe as large and ancient as ours, that's worth celebrating. Thank you so much for listening to this story about one of the most exciting discoveries in modern astronomy. If you enjoyed learning about how the James Webb Space Telescope mapped the 3D atmosphere of a distant planet, please consider subscribing to stay updated on the latest breakthroughs in space science. There's so much more to discover, and we're living in an incredible era of cosmic exploration. Don't forget to subscribe so you won't miss future stories about the wonders of the universe. Clear skies, everyone!